Okay,
now here, let me read out the question. Now, a steel shaft transmitting a transmitting shaft, 510 mm long and 50 mm external diameter. Okay, for part of its length, it is bored, that means drilled to a diameter of 25 mm, and for the rest to 38 millimeter diameter. That means for part of the total length of 510 mm, okay, part of it is drilled to 25 millimeter diameter internal, and then another part is to 38 mm diameter. Find the maximum power transmitted at a speed of 210 revolutions per minute if the shear stress is not to be greater than 70 megapascal. That is part A. Part B, if the angle of twist in the length of 25 millimeter board is equals to that in the length of the 38 mm board. That means the angle of twist for the first section is equals to the angle of twist of the second section. So that means the shaft, you split it into two sections. From 510, you split into two sections. One section which is 25 mm internal diameter. The other part is 38 mm internal diameter. But the external diameter for both the part, for both the section is the same, that is 50 mm. And then the angle of twist, they say for both the section is also the same. So they ask us to find the length bored to the later diameter. That means we have to find out the length for the 38 mm or the 25 mm. Okay, once you found out the length for the 38 mm, of course, you can find out the length for the 25 mm bore. Okay. So this is the diagram. So I have drawn the diagram. So this is the total length, 510 millimeter. So you have internal diameter 25 and internal diameter of 38 mm. Okay, but the external diameter for both the section is 50 mm. So 25 mm diameter is through one section here, and then the second part, which is okay 38 mm, is somewhere around here. Okay, so we know that for hollow shaft, the polar moment of inertia is this. That is the external diameter and the internal diameter. So the external diameter will be basically 50 mm. Internal diameter, it depends on whether you refer to the 25 or the 38. Okay. So what we can do is we can apply the principle of superposition over here. So I hope you still remember what is a principle of superposition based on your mechanics of engineering materials. Okay, so let us consider this to be blank L1 and this is blank L2. And then we put it as A, B, and C, section A and B, that is based on this diameter, internal diameter 25 mm, and then section BC that is based on 38 mm internal diameter. So split it up into two parts. Okay, so the top here, how are you going to convert this? Okay, the top to linear like that. So you can use either your right hand or your left hand for both. Okay, flipping over the shaft. Okay, it will show you the direction of the rotation of the shaft. So basically, when you refer to section B here, that is 0. T is equal to 0. So what we do is we take T here from section C for the equilibrium of the section. If this is T, this should be T. Okay, and then when you consider section BA, that is BA. So if this part here, T is 0, so you have the T here, okay, in this direction. So you have to take another T, which is in the opposite direction, so that this minus this will give you a 0 here. Okay, so that is why for the second section, that is AB, you have the top, okay, pointing this direction opposite to this. So when you take this minus this, it will give you 0. But then section A, of course, if this T here is pointing this direction, then the T or the section A should be in the opposite direction. Okay, so this is based on principle of superposition. Basically, when you refer to this, okay, you got to know that the torque transmitted by section BC and the torque transmitted by section AB, they are the same. They are the same. So based on section AB, so this is the polar moment of inertia, 54 minus 25 power 4. Because this section here, the internal diameter is 25. But then the external diameter for both sections actually is the same, that is 50 mm. So based on this, you can find out the second moment of area or the polar moment of inertia. Then you find the polar moment of inertia for the section BC as well. So you got, okay, the external still 50 mm, but the internal diameter now is 38 mm. So you have 38 here. Remember, this is over 62, yeah, over 62. 32, 32, and it is not 64, yeah, 32. Okay, 64 is for bending, 32 is for twisting moment. So the JBC is 0.41 times 10 to the power 6 mm4, the polar moment of inertia. And for section AB, okay, we apply this formula, which is the strength relationship. Okay, the torque transmitted, the polar moment of inertia, the shear stress, and the radius. Of course, this refers to the maximum radius, yeah? So that is the 25 mm. Okay, so first thing is you can substitute your J here over this part here, and then you know the external radius is how much. So from this, you will be able to actually find out the torque transmitted by section AB. So assuming that the shear stress is at its maximum when the R is maximum. So you have to assume that the shear stress is maximum. So the radius, therefore the radius that we have taken is also maximum. That is 25 mm. 25 mm, that is half of 50 here. Not this 25. This 25 is the internal diameter. So this radius here is actually referring to the maximum diameter over 2 because it's radius. So initially, we consider RAB and RBC to be the same, okay? So when the R is the same, then the shear stress, of course, will be the same, okay? So we have, based on our theory, we know that if we consider maximum shear stress, we would have to consider maximum radius. If we consider minimum shear stress or minimum radius, what we got will be the minimum shear stress. That is basically based on the theory. So from here, we will be able to find out the torque. Now this 0.575 refers to this. Now this is 10 power 6. How come this is 10 power negative 6? Because here I have converted it to meter. This is in millimeter 4. This is in meter 4. Why I have to convert this to meter power 4? Because the 70 here, the shear stress, is meganewton per meter square. Is in meter. So this one and this also must be in meter. Both of these must be in meter. So therefore, you can find out the torque, which is in meter, Newton meter, which is 805. Now, basically, we know that actually in theory, okay, that both the radius are different, okay, are different. So therefore, what we can do is, okay, we work out both the torque first, because both the radius, the internal radius is different, but the external radius should be the same. But then what we can do here is, okay, we try to use both the polar moment of inertia here, both the polar moment of inertia here. Because the radius, you can see the radius are the same, the outer radius are the same. But here we have two different polar moment of inertia. One is for internal diameter 25, the other one is for internal diameter of 38. So basically, we have two different polar moment of inertia. Therefore, that is why when we work out, also we will have two different torque. One is based on this moment of inertia, polar moment of inertia, and the other one is based on this polar moment of inertia. But we know that the shear stress would be the same because actually we are referring to only one outer radius, because section AB and section BC both are having the same external radius, the external diameter and the external radius. So based on the different polar moment of inertia, that is why you got two different torque. One is based on section AB, the other one is based on section BC. Now, if let's say, for example, we found out two different torque, okay, what we can do. Since for the shaft is in series, each part of the shaft should be subjected to the same torque. Okay, same torque. Which torque? Okay, so either we can only use this or we use this. Okay, but since we got two different J, so that is why there are two different torque appears. But when we know that the shaft, they are connected in series, especially when you refer to your principle of superposition just now, you found out that the torque transmitted should be the same. Okay, so that is why we assume that TBC and TAB, that is, therefore we assume that TBC equals to TAB, that is 574, because there's only one torque we can consider, they're not two different torque. So therefore, we consider the maximum 574. Now, once we consider the 574, then we try proof that the torque transmitted is safe or not. That means the 574 and just now the one, the value is, the other value is 805. 574, 805. Now we have to choose which one is safe. Which one is safe to be transmitted. So first one, we assume 574 first to be the same for both. Okay. So what we can do is we substitute the torque inside, because then we are using the same formula. Shear stress tau over R equals to T over J. We use the same formula. But this time we try putting in both the torque and check out the shear stress. See which shear stress will be safe. Okay, so first thing we put 574. And we found that the shear stress of AB is 49.9 megapascal. So that means it's less than the maximum 70 MPa that they have given. It's less than the 70 MPa that they have given. So that means if I consider torque 574 is safe, it is safe. But then if let's say, for example, okay, so the 574 that I adopted, then I put it back, I still get the shear stress 70 equals to 70. So it is safe if I consider the torque transmitted to be 574. That means you cannot transmit any torque that is greater than 574. Okay? You cannot transmit any torque that is greater than 574. If you transmit any torque that is greater than 574, the whole shaft assembly will fail. Will fail. So then you check for section AB. Okay? By using 805 now. So just now we used 574, right? 574. Now we try using 805. So when we use 805 for section AB, no problem. It's still remaining at 70 MPa. Okay? But then if let's say, for example, this should be BC, sorry, this should be tau BC already. Shear stress in BC, shear stress in BC. So if you don't mind, I need to change a bit. Hold on. So now, you see, when we consider for section BC and we use the top of 805 also, okay, so and then we check for section BC. If I use the top 805, section BC can transmit or not. Section AB, no problem, can transmit 805. But section BC, how to transmit 805? When the shear stress is more than 98.2, which is greater than 70. So that means it's failed. It fails. So 805 we cannot consider. We can only consider the top of 574. So you have to be careful when you consider, okay, when you design something, then you theoretically you found out two different top. So from that two different top, basically based on that two different top, which is the maximum top that the shaft that a design can transmit. So you have to check like that, okay? And then you got to know that, okay, 805 I cannot take. I have to take 574. That means my shaft that I designed can only maximum transmit that much of power based on that top. So I cannot transmit any power that is more than that based on the top. That means I cannot transmit any top that is greater than 574. What happens if I insist to supply power more than that? Okay, to supply power more than that, what happens is your shaft will shed, your shaft will snap, okay, will break, because the shear stress that induced is 98.2. So that means the shaft is unable to withstand that amount of shear stress. Do you get what I mean? Okay. So based on 574, so our design will be based on 574. So that is the safe power to be transmitted. So 574 based on the speed of 210, the speed is given, yeah, in the question. So I will be able to find out the safe power to be transmitted is 12.62 kilowatt. Then part B, if the stiffness relationship is the same, they say, for both AB and BC, find out the length. So we know the torque already. Which torque we use is the 574 torque. Okay, the torque to be used is 574. So the J, of course, will be two different sections, AB and BC. So the G, that is the shear modulus, and the angle of twist for both are the same. So if angle of twist of both AB and BC is the same, we try to make theta here to be the subject. Try to make theta to be the subject. Okay? So now, if theta is the same, okay, theta is the same, you can actually put theta as to be the subject, and then you can equate the theta for both. Okay, the theta for both. And then we know that the torque is also the same. Okay, the torque is also the same. The G for both the shaft is made out of same material. They are made out of same material, so the G will be the same. And then part B of the question, they say the angle of twist is the same. Then the torque transmitted across AB and section BC has to be the same. So you can just strike off the T, the G, and the theta. So you got J over L ratio is equals to a constant. So the constant can be section AB, can be section BC. So I hope you understand this equation here. Once you got to know that T over G theta, all these three parameters are constant. So section AB and section BC, the J over L for BC equals to the J over L for the section AB. So based on this, you substitute the J, then you can find out the ratio of LBC to LAB. So you got this. Once you got this, we know that the total length is 510, right? So you put this 0.71304 LBC into this, so that you have only one unknown, that is LBC. Okay? Only LBC. So you add it up, so it becomes 1.713. Okay? So bring this whole thing over, so you have 510 divided by 1.713. So the LBC now you found out is 297 mm. So that means you can have a length of BC section of 297 mm, and for section AB 213 millimeter. Okay, everyone, hope you understand what I've said. Okay, this is the end of this part. Okay, so we'll be continuing with the next part. Okay, any questions?
No.